Okay, welcome to our second video lesson for our unit on Earth structures and processes. This video lesson is going to be about plate tectonics. So what do things like volcanoes, earthquakes that open up huge rifts in the earth, what do they have in common? The idea is that all of these different geological features are made because of plate boundaries. Those are those yellow lines that you're seeing right here. So before we get too far into plate tectonics, we need to know about the layers of the Earth. So the theory of plate tectonics combines the ideas that we've already talked about, which are continental drift and seafloor spreading, and it unites them into a single theory. So according to this theory of plate tectonics, Earth's crust and part of the upper mantle are broken into sections called plates. Those are the plates for our plate tectonics. So we can have two actual kinds of plates. The first kind are our oceanic plates. They make up our oceans. If we go back to this slide, you can probably pick out the oceanic plates, such as our Pacific plate right here. So these oceanic plates, they're older, they're colder, and they're more dense. Our continental plates are our plates that are made up mostly of land, such as our North American plate. Continental plates are going to be newer and they're going to be less dense. And all of these plates are moving around on a semi-liquid layer of the mantle. And we're going to get to our layers of the Earth in just a second. But the plates can be thought of as rafts that are floating and they're moving along on this layer. So we've talked about the crust, we've talked about the mantle, but what actually are these layers? So let's take a look at that now. So our very outer layer and the very thinnest layer is the crust. That's the outermost layer that we live on. It's what we build our buildings on, what we drive on. It's very thin. If you look at this diagram right here, you can see it's by far the thinnest. I want to say 10 miles or so is the thickest part of the crust. So if you compare it to the rest of the Earth, it's a really, really small part of it. If we go in a little more, we get to the mantle. And that is that semi-liquid layer where our lava comes from. Remember, the semi-liquid layer is also what our crust floats on. It's what our plates float on. So going a little deeper still, we get to our outer core. So the outer core is a liquid layer that's mostly molten iron and nickel, where molten is another word. It means that it is melted. So we go all the way to the inside and we find the inner core. Now the inner core is under so much pressure from all of this weight pressing on it that it is a solid metal sphere. It's a solid ball of nickel and iron. So if you'll notice, the outer core is also nickel and iron, but the inner core is deeper inside of the Earth. It's under more pressure, and that makes it solid. So going back to our idea of plates. So the plates themselves are made of crust and a firmer part of the upper mantle. So these divisions between the layers are not quite as nice and neat as they look on this diagram. There's, some transition room. It's not immediately an end to the crust and the mantle begins. These parts together are called our lithosphere. And lithos is Greek for rock, so that should be pretty easy to remember. So lithosphere is our crust and our firmer part of our upper mantle right here. So below this lithosphere, it's more liquid-like. So our mantle is more fluid, it's more liquid. That part is called our asthenosphere. Asthenosphere. And our lithosphere, remember lithos being Greek for rock, our rocky upper layer is floating on this more liquid layer of the mantle, this more liquid asthenosphere. So let's talk about some of these plate boundaries. So plates are massive. They're huge chunks of land that are the size of continents or oftentimes larger. The Pacific plate is by far the biggest plate. So when these huge chunks of rock are moving all around the surface all the time, even at low speeds, they're going to occasionally collide. And these collisions, because even though they're at slow speeds, because they're huge pieces of land, those small collisions give huge impacts. And that's what can create mountains, it can create volcanoes, it can create earthquakes, tsunamis, it can lead to all sorts of things. So not only can plates collide, but they can also pull apart or they can slide alongside each other. So if new crust is being added at one location, why does the Earth's surface not keep expanding? The Earth is pretty much a fixed surface. We're not really adding extra land onto it. And the idea is that as crust is added in one place, it's going to disappear below the surface of another. So this disappearance of crust can occur when the seafloor cools, it becomes denser, and it sinks. So when an oceanic plate converges with a less dense continental plate, remember the continental plates are younger, they haven't cooled down as much, so they're not as dense. So that denser oceanic plate is going to subduct or sink down below into the mantle. So as the plate is subducting into the mantle, it melts and it turns into magma. And magma can be forced out of a volcano, and that's going to create new rock in a cycle. Where the plate subducts into the mantle is called the subduction zone. So I know I threw a lot of words at you just now. So let's take a look at a video and see if we can explain some of this.
The surface of the Earth is made up of many rocky plates. Some of these plates are large and some are small. They are called tectonic plates. Tectonic plates move and can collide into each other at plate boundaries. If one plate moves beneath another plate, extreme temperatures are generated. This is known as a subduction zone. As the temperature increases, rock begins to melt to become magma. Magma is less dense than the surrounding rock, so it begins to rise to the surface, collecting in magma chambers. Volcanic eruptions occur when the magma from these chambers reaches the surface.
Okay, so like I said, plates can do a variety of different actions. So the first is that plates can actually move apart, and that's called a divergent boundary. So you've got two plates right here on each side of this ridge. One's moving to the left, one's moving to the right. That's a divergent boundary. So the North American plate is actually moving away from the Eurasian and the African plates. They all lie along divergent boundaries. So in Africa, the Great Rift Valley, which we're about to watch a video on, might actually become a new divergent plate boundary. The African continent is literally ripping in half.
To understand why this revolution happened, it's necessary to delve deep into the tectonic story of the Rift Valley.
Geologists come to the East African Rift because it's the largest tear affecting any plate on the planet. It's a huge wound which is opening up.
That wound arose because the African plate lies above a huge plume of magma that's slowly melting the crust, causing it to stretch or rift. On the edges of warmed rock, high shoulders rise up. In the middle, the floor subsides, forming a rift. Three million years ago, repeated rapid swings of climate from wet to dry caused huge lakes to form and suddenly disappear. Combined with frequent volcanic eruptions and earthquakes, our ancestors faced unbelievable odds. For Nick, it's part of a greater truth that he's exploring, that the Great Rift Valley is unique. Things happen here that happen nowhere else.
So our second type of plate boundary movement is when plates actually do run into each other. And that's what we call a convergent boundary. So when those two, if you think of two continental plates colliding, because they're less dense than the asthenosphere that they float on, they can actually crumple up. And that's where you get mountain ranges. So for a volcano to form instead of a mountain, there has to be subduction. And remember, subduction is when one plate tucks down below the other, just like this. So this is why volcanoes are typically found near boundaries between oceanic and continental plates. If you've ever heard of the Ring of Fire, that's around the Pacific plate. So our third type is when plates actually slide past each other. So this is called a transform boundary, and that's where they slide past each other. So they can either move in opposite directions, such as this diagram here, where I've got one sort of coming back towards me and one going away from me, or they can move in the same direction but at different speeds. So earthquakes occur when one plate suddenly slips past another. So if you press both your hands in front of you and you press towards each hand but try to move one past each other, it's kind of hard. But if you keep trying, eventually one of them will kind of fly past the other one. That's the same idea as what's happening here. Is you have all this tension built up, but eventually one of those plates slips past the other. That's where you get an earthquake from. So a particularly active transform boundary and the site of lots and lots of earthquakes is actually the San Andreas Fault in California. So let's take a look at that.
These giant gashes in the Earth are reminders of our planet's awesome power. They are fault lines, fractures in the Earth's crust where huge slabs of rock slowly grind past each other. Most faults we can't see, but here in California, the San Andreas Fault is visible at the surface.
You can't have an earthquake without a fault. And I'm standing right now on what is perhaps the most famous fault in the world, the San Andreas Fault, that extends from Mexico down south, way up to Oregon in the north. This is one of the few places in the world where you can stand with one foot on one tectonic plate and one on another. In other words, this ground here is attached to New York and Iceland. The ground here is attached to Hawaii and Japan.
The San Andreas Fault sits on the boundary between the North American and Pacific plates. It's called a strike-slip fault, a place where two plates collide and try to slip past each other. As these plates move or creep in different directions, sometimes they get stuck. The longer they stay stuck, the more tension builds and the bigger the eventual quake. In other places, the plates move smoothly past each other. These areas buckle as the Earth shifts. The changes are subtle. Roger Bilham keeps track of these changes with his creep meter, a device that measures movement along the fault. A computer collects data every minute for a year. This jump in the graph tells him the Earth shifted about 5 millimeters in a couple of hours. A small shift like this can have huge consequences for us.
That might not seem much, 5 millimeters, but it's affecting a long section of the fault, maybe 5 miles long, involving millions of tons of rock. Now, it really doesn't matter here. This is a nice sort of field that aren't any people, but further north, this creep process and the things that are happening beneath the Earth are far more sinister.
The San Andreas Fault and its branches trigger more than 10,000 quakes a year. Sometimes the results are devastating. Just ask the people of Los Angeles or San Francisco. Over the last 2 decades, major quakes rocked both of these cities. Life goes on, but the risk remains. In an area this active, the next violent tremor could happen at any time.
So the cool thing about the San Andreas Fault and the Great African Rift Valley are that both of these things are actually places in the Earth where you can physically see a fault line or a plate boundary. Normally you can't see these things. There's a fault line that runs halfway through Somerville. Can't see it, but with these two, they're very, very visible, as you saw in those videos. So to sum up what we've been seeing, let's see if we can get these 3 types of plate boundaries
This is
down
planet
pat.
Earth. The surface of Earth may look like it's all in one piece, but it's not. It's actually made up of several pieces called plates. Let me explain. Okay, so if you cut the Earth in half, this is what it would look like. The Earth is made up of 4 main layers, like a big round cake. The inner layer is called the inner core, which is a hard ball of hot metals. Around the inner core, there's the outer core, which is made up of very hot liquid metals. Then there's the mantle, which is made up of really hot melted rock, called magma. Sometimes, magma will come to the surface as lava in volcanoes. The 4th layer is called the crust. Like the crust of a piece of toast, the crust of the Earth is the hardest and outermost layer of the Earth. We live on the crust. Crust is not a perfect ball. It is broken up into many pieces called plates. These plates fit together like puzzle pieces around the Earth. Now if you look at the map, you can see where the plate boundaries are. These plates are called tectonic plates, and these tectonic plates can move. This is the world today, and this is what scientists think the world looked like 300 million years ago. This landmass is called Pangaea, and over time, the plates moved slowly apart. They moved at about the speed that your fingernails grow, so it took a very long time for them to get to their present position. Remember the mantle from earlier? Well, the mantle is the layer of Earth right below the crust, and it is made of hot melted rock. This melted rock moves around the mantle, and since it's right below the crust, when the mantle moves, the tectonic plates of the crust move as well. The plates move in 3 ways. They converge, that means come together. When this happens, one plate subducts or goes under another plate and it melts back into the mantle. This happens very slowly. Again, about as slow as your fingernails grow. And it happens mostly in oceans, so you don't have to worry about any land getting subducted anytime soon. When 2 continental or land plates come together, they form mountains. This is how the Himalayan mountain range was formed in India, the tallest mountain in the world. It formed when 2 plates crashed together and crumpled up, sort of like how a car crumples when it hits something big. The second way that plates interact is at divergent boundaries. This is where plates diverge or move apart. And this is also how oceans form. As Pangaea began to break up and the Americas began to move farther away from Africa, the Atlantic Ocean formed in between the continents as their plates diverged. In the middle of the Atlantic Ocean, you can see the Mid-Atlantic Ridge. This is where the North American and Eurasian plates meet, and this is where they are being moved apart. Here, New ocean crust is formed, which pushes the Americas and Europe about 1 inch farther apart every year. The third way that plates can interact is at transform faults. A transform boundary is when two plates are not moving together, or converging, and they're not moving apart, or diverging. Instead, these plates simply slide next to each other. This is happening in California right now, along the San Andreas fault line. This is why there are so many earthquakes in California. When the two plates rub together, they shake the ground and make earthquakes. Okay, so let's review. The Earth is made up of layers, and the top layer is the crust. The crust is broken down into tectonic plates, which very slowly move around the Earth because of movement in the mantle, which is the hot layer of melted rock under the crust. The plates move together at convergent boundaries, they move apart at divergent boundaries, and they slide past each other at transform boundaries. The movement of the plates is extremely slow, and there is very little change every year. But over millions and billions of years, you can see big changes in the way the Earth looks. We know all of this because of great scientists who dedicated their lives to researching and trying to learn more about this great planet we call home.
Okay, so on your guided notes, there's a section for you to stop and reflect. And what I want you to do is list and summarize the three types of boundaries, those three types of faults that we've just talked about. So take a moment to pause the video, finish those, and come back to us. So your parents have to put gas in the car to go anywhere, right? These giant plates, they can't just move around without some kind of energy source too. So, believe it or not, it's pretty much the same process that you use to heat soup on the stove. Surprising but true. So, soup cooking in a pot on the stove contains currents caused by an unequal distribution of heat in that saucepan. So, your hotter, your less dense soup is going to be forced upward by the surrounding cooler and denser soup. So as the hot soup reaches the top, it comes in contact with the air, it's going to cool down, that makes it more dense. Because it's more dense and it's cooler, it's going to sink back to the bottom of the pan. That cycle is called a convection current. So a much larger version of that is happening right now, about 10 to 100 miles below your feet in the mantle. And that's driving the movement of a lot of these plates. So in this diagram here, you can see here's a convection cell. So it's one cycle of this convection current. So here is our hotter, our less dense magma, because it's deeper in the earth. It's hotter. It's under more pressure. So as it flows up, it's going to cool down because it's under less pressure. So as it cools down, it gets heavier. So it starts to fall back towards the bottom where it heats up, becomes less dense, and rises again. That creates that convection current that's moving this lithosphere that's on top. So plate tectonics calls a lot of the features that we see on the surface of the Earth. And one of those are fault lines. So fault lines are essentially the same thing as plate boundaries, they're just smaller. So fault lines can occur within a plate boundary. So we are on the North American plate. The closest boundary to us is way out in the Atlantic Ocean. But within the North American plate, there are lots of fault lines, such as the San Andreas fault we looked at, or the fault line that I told you ran through Somerville. So here's where these fault lines come from. Tension forces can stretch and they can pull apart the Earth's crust. That's going to cause giant blocks of this crust to break and tilt and move. So as these rocks break and move along surfaces, a fault line forms. And when I say rocks, I don't mean little pieces of gravel or even big boulders you might see on the side of the highway. I'm talking miles long, huge slabs of crustal rock. So a rift valley, like that awesome Great African Rift Valley that we just saw, and mid-ocean ridges, which form in the ocean, can form where the Earth's crust separates. So that can create a fault line. Something else that plate tectonics can cause are mountains and volcanoes. So if tension forces can pull rocks apart, compression forces can squeeze the rocks back together. When plates come together, the forces, the huge forces generated, are going to cause massive folding and faulting of rock layers. And this folding and faulting can create mountain ranges and it can create volcanoes. So on the left, over here, I've got a diagram of how the Himalayan mountains were actually formed. So if you think back to our Pangea activity where you assembled Pangea based on evidence, you might remember that the Indian plate collided with the Eurasian plate. So India is actually its own tectonic plate. And when it collided, it is much older than the Eurasian plate. Because it's older, that means it's colder, it's denser, that means it subducts under the Eurasian plate. As it subducted, the Eurasian plate collided with it and started forcing, you can see the arrows, it started forcing that rock up. As the rock was forced up, that created the Himalayas. So I mentioned Himalaya, and I also mentioned the Appalachian Mountains. So I was actually in the Appalachian Mountains about a week ago. So this is just a quick picture I snapped on my way up there. But how do these volcanoes form? So we talked about mountains, but where do the actual volcanoes come from? So here's a video that should shed some light on that for you.
A few hundred years ago, scientists believed that volcanoes were burning mountains of fire. Today, we know they're really openings or vents to the hot interior of the planet. About 1,500 volcanoes around the world are classified as active. Nearly 90% of these rest in the Ring of Fire, a band circling the Pacific Ocean. Their location is no accident. While the Earth's surface looks stable, its crust is made up of immense slabs of rock, like puzzle pieces that constantly shift. Where these tectonic plates interact, volcanoes often form. Friction from shifting plates melts the Earth's crust, causing rock beneath the crust to liquefy. This molten rock, or magma, then becomes a volcano by erupting through rifts in the plates. Once magma escapes from the Earth, it's called lava. But not all lava is the same. Running lava flows quickly and forms the gentle slopes of shield volcanoes. Thick, sticky lava doesn't flow as far and tends to form the steeper slopes of composite volcanoes. Composite volcanoes can erupt violently, hurling ash and lava at speeds up to 200 miles per hour. These eruptions sometimes blow away large chunks of the volcano itself. Some volcanoes, like Hawaii's Kilauea, form over hotspots in the Earth's crust, where magma rises in the middle of a tectonic plate. Kilauea is one of the most active volcanoes on the planet and has erupted continuously since 1983. Because Kilauea is a shield volcano, this constant eruption is a gentle one. Lava oozing from Kilauea constantly hardens into new land, making Hawaii the only state that's still growing. Living near a volcano can be hazardous, as the residents of Pompeii learned in the year 79 AD when Mount Vesuvius erupted, spewing superheated ash, poisonous gas, and rocks. This deadly combination, called a pyroclastic flow, is far more dangerous than a lava flow. Vesuvius buried Pompeii, claiming the lives of 2,000 people. Though volcanoes can be deadly, they also provide benefits. Volcanoes created 80% of the Earth's surface, as well as much of the air we breathe today. Volcanoes create rich soil for farming, and many countries harness their subsurface heat to create geothermal energy. Both creators and destroyers, volcanoes prove that beneath its calm surface, Earth remains a living planet, and a restless one.
As the video mentioned, Pompeii is a famous city in Italy that suffered a huge volcanic explosion, very close to the beginning of AD time. So I actually went to Pompeii back in 2005, and here are some pictures from when I was there. So this is where you can actually see Mount Vesuvius in the background. That's the volcano that exploded and flattened the city. So these ruins are ones that they've dug up in recent times. So you can see a lot of destruction, but because of the stone walls and the concrete architecture, a lot of the stuff is still there. This is actually a room where they kept a lot of the preserved things that they found. This is a body. This is actually a body they found that was preserved by the volcanic ash that they dug out. Around it you can see a lot of the pottery and a lot of the decorations that they may have had in their homes. The last video I want to show you is about a volcanic eruption that struck a little closer to home. This is Mount St. Helens, and one man's story about how he survived the eruption.
18th, 1980, the volcano blew its top. Como4's Bob Thronson says Crockett was an eyewitness to what he called hell on earth.
On that Sunday morning, this was the mountain Dave Crockett came to photograph. It is 8:32 a.m.
I knew I had to get out of there. I started down the valley, look at my rearview mirror, and there's just a wall of debris, mud, steam, rocks, boulders, and full-size trees just rolling along. The whole valley's disappearing behind me. Came down here, ended up right here. I was right about here. The whole little area here just disappeared in front of me completely. Just a big explosion of mud and trees, and I was just blocked off. At that point, I just jumped out of my car, grabbed my film camera, and I went right up there, that ridge, where I had a view just over the trees of the mountain, and I could see what was happening. I opened the door and the alarm started going off, but it was kind of the least of my concerns at that point. The ground is moving, I could feel the earthquakes. The wind is being sucked up towards the mountain, towards the blast. By this time you can hear the mountain rumbling. Constant rumbling, grinding, growling sound. I had this huge cloud of material with lightning and blue and purple colors, rumbling to lightning hitting the ground. I had to get away from that.
Dave starts walking uphill, through the steaming mud, through the ash cloud. He turns on the camera and starts to talk.
Oh, dear God, whoever finds this, I don't know. I can't see this, I'm sure it's too dark. I've left the car behind. Rest of the gear, we got one magazine. As you can tell probably from this picture, I'm walking towards the only light I can see on top of a ridge. I can hear the mountain behind me rumbling. It's an enormous mud and water slide came down and washed out the road. I never really thought I'd believe this or say this, but at this moment, I honest to God believe I'm dead. There's really no way to describe those feelings. I feel the ash now in my eyes. It's getting very hard to breathe. Burns to breathe. I'm having trouble talking. Burns to breathe. Burns my eyes. Oh, dear God. My God, this is hell. I just can't describe it. It's pitch black. Just pitch black. This is hell on earth I'm walking through. Yeah, I got the wrong attitude here. This would be something to tell my grandchildren about. Oh, man. The breeze started blowing the ash out, and all of a sudden I realized I could breathe a little better, and I could see a little bit of greenness. It wasn't pitch black. I could see maybe a couple feet. At that point, I took a photograph of myself with a wide-angle lens, held the camera out in front of me, and click, and I had a big smile on my face. I was just covered with ash, just my hair was sticking straight out, but I think you can tell from the expression on my face, I thought then maybe I was going to get out. When I finally realized I had made it and I was going to live, I just started laughing and screaming out loud, and I was just yelling at the mountain.
St. Helens would claim many lives today, but not this one.
Alright, so last but not least, we've talked about how Australia is actually moving. It's moving about 5 inches per year. Doesn't sound like a lot, but for a massive continent, that's a lot. And North America is actually creeping along at only about 2 inches per year. I think one of those videos actually said most plates move about the same speed that your fingernails grow. So not very much at all. But how do we actually know this? How do you go about measuring something like a continent moving? That's such an enormous task. And what scientists have come up with is that we can actually use lasers and a satellite to provide measurements that are accurate to about 1 centimeter per year. So what happens is a telescope actually sends a laser beam up to a satellite. That satellite returns the laser beam to the telescope. And the telescope can sense how far off from where it sent the beam out did it return. That can tell the computer, and therefore the scientist, how fast that continent is moving compared to the satellite. So, go ahead and finish those reflection questions that are at the end of that. If you have any questions, please let me know. I'll be more than happy to come around and get you the help you need.